In this video, we discuss one more example about exact equations. Now we have an initial value problem. So this is a initial value problem. We have a differential equation. We also have an initial condition. So we can get a particular solution for our differential equation, right? Which satisfy the given initial conditions. So we are given the differential equation is given by dy over dx equal to uh, xy square minus cosine of x sine of x and y 1 minus x squared. We also know that y of 0 equal to 2, right? We are looking for what is a function y, right? So that's basically it. So clearly, this is not a standard form of differential, what's that called? Exact equation, right? Standard form of exact equation. You change it, you get y 1 minus x squared dy and minus x y squared minus cosine of x times sine of x dx equal to 0, right? Which you know that in this case, m equal to negative xy squared minus cosine of x times sine of x. And n here is y times 1 minus x squared, right? Now we want to verify this equation exact equation, right? We want to calculate my, the derivative of m about y. So this is negative 2xy. This term here goes to 0 because that doesn't contain y, right? And also n what? Nx also equal to negative 2xy. So this is an exact equation. Now we are looking for f such that df, the differential f is m dx plus n dy, right? So we get, okay, suppose df is m dx plus n dy, I dot e f sub x equal to negative xy squared minus cosine of x sine of x and f of y here equal to y 1 minus x squared. That's it, right? Okay, so we have two equations, 1 and 2. We want to integrate them, right? Start from the one which is easier to integrate. Let's try to start from 2, right? 2, the function is smaller, it looks much easier. So let's integrate 2, right? And 2 here implies f of x of y equal to what? Equal to, that's a constant compared to y. So you get y squared over 2, 1 minus x squared, and then plus a function, a constant, a cost function relative to y. So that should be a function contains only x, right? Now this is our equation 3. So equation 3 here also implies f, so we want to use equation 1. Compare with equation 1. We'll differentiate f about x very naturally. So this is negative y squared over 2 times 2x, right? Then plus h prime of x. And then this is our equation 4 here. So equation 4 plus equation 1, both are about the derivative of f about x, right? So you get negative y squared over 2 times 2x plus h prime of x equal to, let's split, no, let's distribute negative, right? Negative xy squared plus cosine of x sine of x. Now you look at compare both sides, y, the term contains y will be cancelled. So you get h prime of x is cosine of x sine of x. So we choose our h of x is the integration of cosine of x sine of x dx. You can use u substitution, let u equal to sine, and then du is cosine x dx. So you get this is sine square of x over 2, then plus a constant, let's call it c1, right? So then we get a function. So c1 can be anything. We choose c1 to be 0 for sure, right? Easier one. c1 0, we plug h back into here. We get we get we get a particular function whose differential is basically the exact differential, right? So we choose f of x y equal to y squared over 2, 1 minus x squared, plus sine square of x over 2 by setting, again, here you can set c1 be any number you want. We like the c1 to be easy number, be 0, right? And finally, so y squared over 2, 1 minus x squared plus sine square over 2 equal to c is an implicit solution of the dE. But we have an initial condition, right? We know that y of 0 equal to 2. We want to figure out what's c, right? Since y of 0 equal to 2 equal to 2, replace x by 0, then y has to be 2, right? So get 2 squared over 2, 1 minus 0 squared times, no, plus sine square of 0 over 2 equal to c, right? Now you can see that sine of 0 is 0, and 2 square over 2 is 2. So c here equal to 2. So a solution for the initial value problem is y squared over 2, 1 minus x squared plus sine square of x over 2 equal to 2. So that's basically a solution of our differential equation, right? So this is how do we solve it if you are given a exact equation, and this one also has an initial condition. We just need to figure out a function whose differential equal to the exact differential, and by solving a system of differential equations. And then after that, plug the initial condition into the implicit solution, general solution, we get a particular solution which satisfies the initial value problem. Okay.